On the last day of 2004, a spacecraft sent home a photograph that looked edited. A moon of Saturn, half of it black as coal, the other half white as snow. And wrapped around its middle, running almost perfectly along the equator, a wall of mountains taller than anything on Earth. It circles 3/4 of the way around the world, in places rising 13 kilometers, with peaks climbing past 20. No other moon in the solar system wears anything like it. It looks built. It looks deliberate. It looks like a seam holding two halves of a planet together. But nothing intelligent placed it there. Something far stranger did. An event so ancient and so violent that we can no longer directly see what it once was. If you find the strange corners of the solar system as fascinating as I do, it would mean a lot if you tap that like button and subscribed. It honestly helps these deep dives reach more curious people like you. Now, are you comfortable? Let's begin. Imagine the screens in a quiet operations room at the Jet Propulsion Laboratory on the last day of 2004. The Cassini spacecraft had been circling Saturn for only half a year, still settling into its long tour of the ringed planet and its dozens of moons. On the 31st of December, it swung past a distant, little-studied world called Iapetus, and turned its narrow-angle camera toward the surface. The images crawled back across more than 1 billion kilometers of empty space, line by line, and assembled themselves on the monitors. And when the picture finally resolved, the people watching it leaned in because something about the moon looked wrong. Not damaged, not blurred. Wrong in the way a photograph looks wrong when you suspect it has been edited. There, stretched across the middle of the world, was a line. A long, sharp, raised line of mountains running almost exactly along the equator, as if someone had taken a globe and welded a seam around its waist. On one side, the surface was as dark as fresh asphalt. On the other, it brightened towards the poles into something closer to dirty snow. And dividing the dark half down its center, slicing through the blackest terrain on the moon, ran this enormous wall of peaks, casting long shadows in the low sun. It did not look like weather. It did not look like erosion. It looked deliberate. It looked to more than one person staring at the screen like architecture. It is not architecture. Let us be completely clear about that from the beginning, because the rest of this story depends on holding two ideas in your head at the same time. The first idea is that the structure looks, at a glance, like something built, a rampart, a seam, a wall constructed around a planet. The second idea is that nothing built it. No engineers, no machines, no ancient hands. What you are looking at is a natural feature, a mountain ridge, raised by some process in the deep past of the solar system. The strangeness here is not that aliens left a monument. The strangeness is that ordinary physics produced something so clean, so straight, and so perfectly placed that the human eye keeps insisting it must have been designed. Before we can understand how nature could do this, we have to understand exactly what we are looking at. So let us slow down and meet the moon itself. Iapetus is the third largest moon of Saturn and the 11th largest moon in the entire solar system. It is a world of ice and rock, a little over 700 kilometers in radius, which works out to roughly 1,470 kilometers from side to side. That makes it large enough to pull itself into a rounded shape under its own gravity, but small enough that you could lay it across the United States and have room to spare. It is not a giant. It is not Titan, the cloud-wrapped moon nearly the size of a planet that orbits closer to Saturn. Iapetus is the outermost of Saturn's major moons, the lonely one, circling the planet at a distance of about 3.5 million kilometers. That is roughly 10 times farther out than our own moon orbits Earth. From that great distance, Saturn would still loom in its sky, banded and ringed, but the moon spends its existence out at the cold edge of the system, far from the warmth and chaos closer in. Its year, the time it takes to loop once around Saturn, is a little over 79 days. And here is the first quietly unusual thing about it. Iapetus is tidally locked, which means it rotates exactly once for every orbit it completes. The same face always points towards Saturn, in the same way the same face of our moon always points toward Earth. But because Iapetus takes 79 days to circle its planet, it also takes 79 days to turn once on its axis. A single day on Iapetus lasts almost 3 Earth months. The sun rises with agonizing slowness, drags across the sky, and sets again over the span of weeks. We will come back to that long, slow rotation later, because it matters more than it first appears. For now, simply hold on to it. This is a world that turns with extraordinary patience. The moon was discovered long before any spacecraft could photograph it. In the year 1671, the Italian-born astronomer Giovanni Cassini spotted a faint point of light near Saturn through his telescope. It was the first moon he would ever discover, and it behaved oddly. Cassini could see it clearly when it sat on one side of Saturn, but when it swung around to the other side, it seemed to vanish, fading below what his instrument could detect. From this single strange behavior, Cassini reasoned his way to a remarkable conclusion. He decided that the moon must have one bright hemisphere and one dark hemisphere, and that it must always keep the same face turned in the same direction as it traveled, so that we see the gleaming side at one point in its orbit, and the blackened side at another. He was right. More than 3 centuries before any probe arrived, a man with a hand-built telescope had deduced both the two-tone surface and the locked rotation of a moon he could barely see. The largest dark region was eventually named in his honor, Cassini Regio. That two-tone coloring is the feature Iapetus was famous for, long before anyone knew about the wall. The difference between the two halves is the most extreme of its kind anywhere we have looked. The dark leading hemisphere, the side that faces forward as the moon plows along its orbit, reflects only about 3 to 5% of the light that strikes it. That is darker than coal, darker than a fresh asphalt road, one of the blackest large surfaces in the solar system. The bright trailing hemisphere and the poles, by contrast, reflect somewhere between 50 and 60% of the light that falls on them, gleaming almost as brightly as the icy moons closer to Saturn. One world, painted in 2 opposite extremes, with a startlingly sharp boundary between them. For a long time, that dramatic split was the headline. The dark side, the bright side. The puzzle of why a single moon should be divided so cleanly. We will touch on what causes that coloring later, because it adds to the moon's strange identity. But the coloring is not our subject. Our subject is the line that runs through it. Because when Cassini's cameras finally got a clear look at the dark hemisphere on that last day of 2004, they revealed something the old telescopes never could. Running straight down the center of Cassini Regio, hidden for centuries in terrain too dark for earlier instruments to resolve, was the ridge. And the moment you see its dimensions written out, you begin to understand why people reach for words like impossible. The most prominent, continuous stretch of the equatorial ridge runs for about 1,300 kilometers across the dark hemisphere. though related mountains extend much farther around the moon beyond it. It is roughly 20 kilometers wide at its base, and it rises, on average, around 13 kilometers above the surrounding plains, with individual peaks climbing higher still, more than 20 kilometers up from the terrain below. Let those last numbers settle, because they are difficult to picture. Mount Everest, the tallest mountain on Earth measured from sea level, reaches not quite 9 kilometers into the sky. The peaks of the Iapetus ridge stand more than twice as tall. On a moon less than a third the width of our own planet, nature raised a mountain range that towers over anything Earth has ever produced. These are among the tallest mountains found anywhere in the solar system, and they sit on one of the smaller worlds capable of holding them. Now hold that scale in proportion. On Earth, the tallest mountains are tiny compared to the size of the planet. If you shrank the Earth to the size of a billiard ball, it would feel smoother than the ball does, mountains and all. But Iapetus is a small world, and its ridge is enormous relative to that small body. The wall rises so high, relative to the moon's modest size, that it visibly deforms the entire shape of Iapetus. Seen from a distance, the moon does not look like a clean sphere. It bulges at the equator and flattens at the poles, swollen along its middle by the ridge and the broad rise of rock and ice beneath it. Scientists describe the overall result with a word that has stuck: walnut. Iapetus is shaped like a walnut, a rounded body with a raised seam wrapping its waist. No other large moon in the solar system carries a shape like this. The ridge is not a detail sitting on the surface. It is large enough to define what the whole world looks like, but a single number can mislead you. So let us describe the wall more carefully, because precision is the whole point here. The ridge is not one smooth, unbroken band circling the entire moon like a hoop. It is a complex system. In places, it forms a single towering crest. In other places, it splits into 2 or even 3 parallel ridges running side by side, like the folds of a crumpled cloth. Elsewhere, it breaks down into chains of isolated peaks, individual mountains standing in a rough line where the continuous ridge has been interrupted or destroyed. 3 major sections of it have been given names: Tortellosa Montes, Toledo Montes, and Carcassonne Montes, stretches of mountains that together trace the moon's midsection. Some of the brightest of these peaks, near the edge of the dark region, were actually glimpsed decades earlier. When Voyager 2 flew past Iapetus in August of 1981, its cameras could not see into the black heart of Cassini Regio, but they caught a few pale mountains poking up near the boundary. Observers nicknamed them the Voyager Mountains, without realizing they were seeing the bright tips of a structure that would not be fully revealed for another 23 years. In fact, those very peaks were captured in a way no one understood at the time. When Voyager 2 imaged Iapetus's North Polar region in August of 1981, the mountains registered only as a faint scattering of light and dark dots strung along the equator, right at the limit of the camera's resolution, easy to dismiss as noise. No one watching could have guessed those specks were summits, still less that they belonged to a single continuous structure wrapping the moon. Only after Cassini revealed the full ridge did their meaning fall into place. They were the crests of the wall, catching sunlight and throwing shadow, recorded a full quarter of a century before the feature they belonged to was understood. The evidence had been sitting in the archive the whole time, waiting for a sharper eye to recognize it. So how much of the equator does this wall actually follow? This is where we have to be careful and honest, because the answer is striking enough without exaggeration, and exaggeration would only weaken it. The ridge does not encircle the entire moon. It follows roughly 3/4 of the way around the equator, about 75% of the circumference, concentrated heavily in the dark hemisphere of Cassini Regio. In the bright hemisphere, the continuous ridge fades into scattered, isolated peaks, rather than an unbroken crest. So when you hear that Iapetus has a wall around its equator, the accurate picture is this: a mostly continuous mountain system, broken into segments, that traces the great majority of the moon's midline before thinning out on the far side. That is still astonishing. A natural mountain range that follows 3/4 of a world's equator, almost without wandering off it, is something we have found nowhere else at this scale. But it is a ridge that follows the equator, not a solid hoop welded all the way around. The difference matters, and we will see exactly why it matters in a moment. There is one more observation that turns out to be enormously important, and it concerns the age of the wall. When planetary scientists want to know how old a surface is, they count craters. The longer a surface has been exposed to the constant rain of impacts that pepper every body in the solar system, the more craters it accumulates. And the ridge of Iapetus is heavily cratered. Its slopes and crests are pockmarked, scarred, battered by impacts. Whatever raised this wall, it did not happen recently. The ridge is ancient, dating back to the early history of the moon, deep in the first chapters of the solar system's existence. This is not a young, fresh feature. It is a relic, a survivor that has been standing on the equator long enough to be hammered by billions of years of cosmic bombardment, and still remain. We will come back to the craters in detail later, because counting them carefully turns out to offer one of our best clues to how the ridge formed. For now, the headline is simple. The wall is old, and it has been standing on the equator for almost the entire life of the moon. Let us also give the rest of Iapetus its due, briefly, so you can see the ridge in context. This is a heavily cratered, geologically quiet world. It carries enormous impact basins, gouged out by collisions early in its history. Several of them more than 350 kilometers across. The largest, a basin named Turgis, spans roughly 580 kilometers, with a steep rim that drops in places by more than 10 kilometers. The moon also shows evidence of vast landslides, where material has slumped down crater walls and run out across the surface in long, smooth tongues, possibly lubricated by sliding ice. In other words, Iapetus is not a featureless ball. It has a rich and battered face, but every other feature on it, the basins, the slides, the dark stain of Cassini Regio, sits on a body that is otherwise unremarkable in its overall shape. Only the ridge distorts the whole moon. Only the ridge wraps the equator. Only the ridge makes Iapetus look, from across the void, like a world that has been built rather than born. Cassini would return for a much closer look. On the 10th of September 2007, the spacecraft made a targeted flyby, sweeping in to within about 1,200 kilometers of the surface, low enough to resolve features only tens of meters across. Those images are the ones that truly sharpen the picture. They showed the ridge rising in steep, rugged slopes, in some places cut and terraced, in others crowned by sharp summits. They confirmed the heights. They confirmed the equatorial alignment. And crucially, they ruled out the easy, comforting explanations. At that range, Cassini did more than confirm the ridge existed. It began to render the wall in something approaching 3 dimensions. By imaging the same terrain from slightly different angles, the spacecraft allowed scientists to reconstruct the relief of the mountains, to measure their true heights, to trace the steepness of their flanks, to see where the ridge rose as a single crest and where it split into parallel folds. The summits resolved into rugged, sharply shadowed peaks. The slopes showed terracing and signs of material that had slumped downhill over the ages. These were the views that converted a startling silhouette into a measurable landform. They showed the ridge rising in steep, broken slopes, crowned in places by individual mountains, and they pinned down the dimensions that every later theory would have to explain. This was not a trick of lighting. It was not a coincidental row of unrelated peaks. It was a coherent, continuous, mountainous structure following the equator of a moon, and nothing else in our catalogue of hundreds of known moons looked anything like it. So now we have to confront the question the wall forces on us. What does it mean to call this a wall in the first place? Because the word carries baggage. A wall, in human language, suggests a barrier, something solid, vertical, and built to divide or defend. The Iapetus Ridge is none of those things in that sense. You could not walk up to it and find a sheer face like a fortress rampart. It is a mountain range. Its flanks slope, its crest is broken and uneven. If you stood at its base, it would look like standing at the foot of a colossal mountain chain, not a constructed barricade. The wall is a description of how it appears from space and what it does to the moon's outline. A raised band circling most of the waste of a world, not a claim about its nature. When this episode promises you a moon with a wall around its equator, that is the wall it means. A natural mountain ridge of staggering height that traces 3/4 of the equator with the precision that looks, to our pattern-seeking eyes, unnervingly deliberate. And that brings us to the precise edge of the mystery. The thing that separates Iapetus from every other strange object in the solar system. It is tempting to think the remarkable fact about this ridge is its height. 20-kilometer peaks on a small moon. Surely the size is the marvel. But it is not. Tall mountains on their own are not deeply mysterious. We can explain tall mountains. Mars has volcanoes that dwarf even this. Worlds with low gravity and rigid crusts can support enormous topography precisely because there is so little weight to drag it back down. If the only unusual thing about Iapetus were that it had very tall mountains, this would be a footnote, not a riddle. The height alone would not have made anyone in that operations room lean toward the screen. What made them lean in was the line. It was where the mountains sat. Not scattered across the surface the way mountains scatter on every other world we know. Not clustered around impact sites or volcanic centers or fractured terrain, but arranged in a long, raised band that hugs the equator. The one specific circle on the entire moon where the spin axis says the equator should be, and follows it for 3/4 of the way around the world. On Earth, mountain ranges run wherever colliding plates and rising magma happen to push them, in jagged, wandering chains that pay no attention to latitude. The Andes do not follow the equator. The Himalayas do not follow the equator. Mountains, as a rule, go where the forces of a planet send them, and those forces care nothing for where the equator happens to lie. Yet here is a mountain system that appears to care about almost nothing else. It clings to the equator as if the equator were a track laid down for it to follow. That is the real puzzle, not the height of the wall, but its address. A mountain range that just happens to trace the equator of a world is not the kind of thing nature is supposed to be able to do by accident. The equator is not a special place on a surface. It is not a fault line, not a seam in the crust, not a vein of any particular rock. It is an imaginary circle defined entirely by the way the moon spins. For a real, physical mountain range to align itself with that invisible line, something must have connected the building of those mountains to the rotation or the orbital motion of the entire moon. And the moment you realize that, the question stops being, where are the mountains, and becomes something far stranger. Why does a wall of rock know where the equator is? That single question is the door into everything that follows. In the next part, we will step through it. We will look at why equatorial alignment is the most important clue we have, why it transforms an unusual mountain chain into one of the genuine unsolved problems of planetary science, and why the three blunt facts about this ridge, that it sits on the equator, that it sits only on the equator, and that it sits, so far, only on Iapetus, narrow the list of possible explanations down to a small and very specific set of suspects. Because once you accept that the wall is tracking the spin of the moon, you are no longer looking for whatever pushes up ordinary mountains. You are looking for something that once wrapped itself around this entire world. We are left then with a question that sounds almost playful until you really sit with it. Why does a wall of rock know where the equator is? Say it out loud and it seems like a strange thing to ask. Mountains are mountains. They are heavy, stubborn piles of rock and ice. They do not have eyes. They do not consult a map. And yet here, on this one distant moon, an enormous mountain system appears to have done precisely that. To have found the equator and followed it, faithfully, for 3/4 of the way around an entire world. To understand why that single fact has occupied planetary scientists for 2 decades, we have to understand what the equator actually is, and why a mountain range agreeing with it is so much stranger than a mountain range simply being tall. Start with the equator itself. It is tempting to think of the equator as a real, physical place, a line you could trace on the ground, a belt of distinct terrain. It is not. The equator is an idea. It is an imaginary circle drawn exactly halfway between a world's two poles, defined entirely by one thing and one thing only: the way that world spins. Take the axis a planet or moon rotates around, the invisible pole running through its center. Now slice the world in half perpendicular to that axis, at the widest point of the spin. The edge of that slice is the equator. It is not made of any special rock. There is no fault running along it, no vein of unusual material, no seam in the crust. It is a geometric consequence of rotation, nothing more. If a moon stopped spinning and began turning around a different axis, the equator would move to a new place, even though not a single grain of the surface had shifted. The equator is, in the most literal sense, drawn by the way the planet turns. That is what makes the ridge so disorienting. A physical thing, billions of tons of mountain, has lined itself up with a non-physical thing, a line that exists only because of rotation. And it has done so with startling accuracy. Across the dark hemisphere of Cassini Regio, where the ridge is at its most continuous, it tracks the equator to within just a few degrees of latitude. It does not wander north for 1,000 kilometers, and then drift south. It does not cut diagonally across the moon. It hugs the midline like a tightrope walker, who refuses to look down. And the closer a mountain range clings to that invisible, rotation-defined circle, the harder it becomes to explain by ordinary means, because ordinary mountain building does not care about rotation at all. Look at our own planet to feel the contrast. Earth is covered in mountains, and not one major range pays the slightest attention to the equator. The Andes run down the western edge of South America, slicing across dozens of degrees of latitude from the tropics nearly to the icy south. The Himalayas pile up, where the Indian landmass rams into Asia, a collision zone that happens to sit well north of the equator, for reasons that have nothing to do with where the equator is. The Rockies, the Alps, the great mid-ocean ridges hidden beneath the seas. All of them go wherever the planet's internal forces shove them. On Earth, mountains are built by colliding plates, by rising plumes of molten rock, by the crust buckling and tearing under stresses that originate deep inside. None of those forces know or care which way the planet is spinning. They build mountains in jagged, meandering, accidental chains that sprawl across the globe in every orientation imaginable. If you mapped every mountain on Earth and asked whether they preferred the equator, the answer would be a flat no. They are scattered like cracks across a dropped plate. So the alignment on Iapetus is not just unusual. It is, in a precise sense, improbable. Think of it this way. There are infinitely many great circles you could draw around a sphere, circles tilted at every conceivable angle, passing through every possible pair of opposite points. The equator is only one of them, singled out by rotation. For a long mountain range to appear, and then to land on that one specific circle out of all the possibilities, and to follow it for 3/4 of the planet, is the kind of coincidence that a scientist instinctively refuses to accept as coincidence. When something improbable happens once, you might shrug. When the most improbable arrangement possible is staring you in the face across an entire world, you stop believing it was chance and start hunting for the mechanism that forced it. The placement of the ridge is not noise. It is a signal, and the whole challenge of Iapetus is figuring out what that signal is telling us. To organize the hunt, planetary scientists have boiled the problem down to 3 blunt requirements. Any explanation for this ridge, every theory, no matter how clever, has to satisfy all 3 of them, or it fails. They function like 3 locks on a single door, and a hypothesis that picks only 2 of them does not get in. These 3 constraints are the backbone of everything that follows, so let us state them plainly. The first requirement: the ridge sits on the equator. Whatever process built, it has to explain not just that there are mountains, but that the mountains are arranged along the rotational equator with high precision. A theory that builds a tall ridge in the wrong place is no good. The second requirement: the ridge sits only on the equator. This is subtler and, in some ways, even more demanding. It is not enough to explain how you could pile mountains up at the equator. You also have to explain why there are not similar ridges running elsewhere. No comparable wall along some of the circle, no second range cutting across the poles. The equator got the wall, and the equator alone. A good theory has to explain that exclusivity. The third requirement: the ridge sits, so far as we know, only on Iapetus. Among the hundreds of moons in the solar system, icy moons, rocky moons, giant moons, tiny moons, moons battered and frozen and cracked in 1,000 ways, only this one wears a mountain belt around its waist at this scale. Whatever happened here either did not happen elsewhere, or could not happen elsewhere. So the explanation cannot be some generic process that should affect lots of moons. It has to be tied to something special about Iapetus in particular. Hold those three locks in mind. On the equator, only on the equator, only on Iapetus. Now watch what happens when we test the most familiar mountain building ideas against them, because the failures are as informative as any success. Begin with the everyday explanations. The ones that build the mountains we know on Earth and on other worlds. Could the ridge be a volcanic chain, a line of eruptions that piled up lava or icy material over time? Worlds with frozen surfaces can have a kind of cold volcanism, where slushy ice and liquid water erupt instead of molten rock. But volcanoes go where the heat is, where the interior is melting and pushing upward, and there is no reason on Iapetus for that heat to organize itself into a perfect band along the rotational equator. Volcanism could fail the very first lock. Could the ridge be tectonic? The result of the crust buckling, folding, or cracking under stress? On Earth, this is exactly how long mountain chains form. But again, crustal stresses on a moon do not naturally arrange themselves into a single equator-following line. You could perhaps imagine compression squeezing up a ridge somewhere, but explaining why that ridge would track the equator and only the equator requires extra, special pleading. Could it be a chain of impacts? A row of mountains thrown up by collisions? Impacts strike randomly from every direction. They have no preference for latitude whatsoever. A line of craters along the equator would be a coincidence stacked upon a coincidence. Every one of these ordinary explanations stumbles on the same threshold. They can make mountains. What they cannot easily do is make mountains that obey the spin axis. And that failure is the most important clue in the entire investigation, because it points, by elimination, toward the only kinds of processes that do obey the spin axis. If random geology cannot draw a line on the equator, then whatever drew this line was not random. It was connected somehow to the rotation of the whole moon. This is the turning point of the whole story. So let us make the logic crisp. There are really only two broad ways that a feature on a world can end up locked to its equator, and both of them run through the spin axis. The first way is through the moon's own shape. A spinning body bulges at its equator. Spin anything fast enough, a ball of pizza dough, a planet, a moon, and it flings its midsection outward, swelling along the equator and flattening at the poles. The faster the spin, the bigger the bulge. So one family of explanations says the ridge is somehow a consequence of rotation acting on the moon itself. The body's shape, frozen or fractured or pushed up along the line where spin has the greatest effect. Any such mechanism would naturally respect the equator, because the equator is exactly where a spinning body's shape is most distorted. We will examine this family in detail later. For now, simply note that it satisfies the first two locks almost automatically. A shape effect tied to spin lands on the equator, and only on the equator, because that is where the spin geometry concentrates. The second way is through orbit. Here's a fact that is not obvious but turns out to be deeply important. If material orbits a slightly flattened body, a body with an equatorial bulge, like nearly every spinning moon and planet, that orbiting material does not stay tilted forever. The bulge tugs on it gravitationally, and over time it nudges the orbiting material to settle into the plane of the equator. Rings do this. Saturn's own magnificent rings lie almost perfectly in Saturn's equatorial plane, flat as a vinyl record, precisely because Saturn's bulge has herded them there. So if Iapetus once had material orbiting around it, a ring, a disk of debris, the shattered remains of something, that material would have drifted over time into the moon's equatorial plane. And if that material then came down, raining onto the surface, it would come down along the equator. Not because the equator is special on the ground, but because the equator is where orbiting matter ends up before it falls. This family of explanations, the ones involving something that orbited the moon and then descended, also satisfies the first two locks naturally. Material from an equatorial orbit lands on the equator, and lands only on the equator, because that is the line beneath its path. Do you see what has happened? By insisting on the three constraints, we have quietly narrowed an open-ended mystery down to two suspects, and both of them are connected to rotation. Either the ridge came from the moon's own spinning shape, or it came from something that orbited the moon in its equatorial plane and then fell. Random tectonics, random volcanism, random impacts, all eliminated by the simple, stubborn fact that the wall follows the spin. The equator has acted like a filter, and almost everything has been filtered out. What remains is a short list, and every item on it points back to the way Iapetus turns and the way things move around it. But two locks are not three. We still have to face the hardest requirement of all. Why only Iapetus? Plenty of moons spin. Plenty of moons could, in principle, have had material orbiting them. So why is this the only large moon in the entire solar system with a mountain belt around its middle? If the answer were simply rotation or orbiting debris, we might expect to see at least faint versions of this ridge elsewhere among the great icy moons. We do not. And the answer to that puzzle turns out to be one of the most genuinely special things about this particular moon. Something that sets it apart from every other major satellite in the outer solar system. It comes down to a region of space called the Hill sphere. The Hill sphere of a moon is the zone around it where the moon's own gravity wins. Where the moon's gravitational pull dominates over the much larger pull of the planet it orbits. Inside the Hill sphere, a moon can hold onto things. Smaller satellites, rings, clouds of debris. Outside it, the planet's gravity takes over and strips those things away. The size of a moon's Hill sphere depends on a tug-of-war between the moon's gravity and the planet's. And here is the crucial point. The farther a moon orbits from its planet, the weaker the planet's grip becomes at that distance, and the larger the moon's own zone of gravitational dominance grows. Now recall where Iapetus lives. It is the outermost of Saturn's major moons, circling at roughly 3.5 million kilometers, far, far beyond the busy inner system where the other large moons huddle close to the planet. At that great remove, Saturn's tidal grip on Iapetus is comparatively gentle, and because Saturn's hold is so loose out there, Iapetus commands an enormous Hill sphere. In fact, relative to its own size, Iapetus has the largest Hill sphere of any major satellite in the outer solar system. Its gravitational territory, the volume of space in which it could hold onto orbiting material, is proportionally vaster than that of any other big moon out there. This single fact begins to crack the third lock. Iapetus is uniquely well suited, among the large moons, to have held its own ring or its own small companion satellite. The inner moons of Saturn, locked in close, have tight little Hill spheres. Saturn would tear away any substantial orbiting debris before it could do much. But Iapetus, far out in the cold and the dark, with weak tides and a sprawling gravitational domain, could plausibly have hung onto a ring of material, or a sub-satellite, a moon of a moon, long enough for it to matter. If the ridge was built by material falling from an equatorial orbit, then you need a moon capable of having that orbit in the first place. And of the great moons, Iapetus stands out as the one that could. Its loneliness, its remoteness, the very thing that made it the outermost and most overlooked of Saturn's major children, may be exactly what gave it a wall. There is a second oddity about Iapetus that deepens the case, and we touched on it in the last part. The moon turns with extraordinary slowness, once every 79 days, locked face on to Saturn. That is a far slower spin than most moons, and there are strong reasons to think Iapetus was not always so sluggish. That early in its history it turned much faster, and was gradually brake to its current crawl. A moon that once spun quickly and then dramatically slowed is a moon whose shape and whose orbiting debris would both have been governed by rotation in ways that could leave a permanent equatorial mark. We are deliberately not unpacking that mechanism yet. It belongs to a later stage of the investigation. But it is worth flagging now because it reinforces the central theme. Everything strange about this ridge keeps leading back to the same two things: how Iapetus spins and what once moved around it. The slow rotation, the giant hill sphere, the equatorial alignment. These are not separate curiosities. They are threads of a single knot. And here is where the investigation gets a powerful boost, because we are not reasoning in pure abstraction. We can actually point to other places in the solar system where ridges have formed along equators from orbiting material, and watch the process in miniature. The evidence comes from two tiny moons embedded right inside Saturn's rings, Pan and Atlas. These are small bodies only tens of kilometers across, orbiting within the ring system itself, sweeping through the very material that makes up Saturn's rings. And both of them have equatorial ridges. Each one carries a raised band of material around its middle, so prominent that it gives the little moons a peculiar, unforgettable shape. They look like flying saucers, or like a piece of ravioli, with a smooth bulge wrapped around a central core. Planetary scientists are fairly confident about how those ridges formed. As Pan and Atlas plow through Saturn's rings, ring particles drift down onto their surfaces. And because that material is orbiting in the ring plane, which lies along each little moon's equator, it accumulates along the equator. The ridge is built grain by grain from material raining down out of an equatorial orbit. That is enormously important because it takes one of our two leading ideas out of the realm of speculation and into the realm of observed fact. We do not have to imagine whether orbiting material can pile up into an equatorial ridge. We can see that it does on Pan and on Atlas right now in our own time. The process is real. Material in an equatorial orbit, falling onto a moon, builds a ridge along the equator. The principle is demonstrated. But, and this is the honesty the subject demands, the demonstration is at a tiny scale, and the differences matter as much as the similarities. Pan and Atlas are little moonlets gathering a gentle dusting from a ring that is right there, all around them, supplied endlessly by Saturn. Their ridges are modest swellings. The wall on Iapetus is a mountain system rising more than a dozen kilometers, built on a body far larger and far more distant, with no obvious modern ring anywhere near it to supply the material. So Pan and Atlas prove the concept, but they do not prove the case. They show that nature can draw a ridge along an equator by dropping orbiting material onto a moon. They do not, by themselves, show that this is what happened to Iapetus, where the scale is vastly greater and the ring, if there ever was one, is long gone. The little ring moons are a proof of principle, a glimpse of the mechanism working in gentle miniature. Whether the same kind of mechanism, scaled up enormously and run in the deep past, could build something as monstrous as the Iapetus Ridge is a separate question, and a much harder one. Still, look at how far the simple insistence on location has carried us. We started this part with a mountain range that merely looks strange, and a vague sense that its height was the marvel. We have arrived somewhere much more specific. We now understand that the height is almost beside the point, and that the true mystery is the alignment, a physical structure obeying an invisible line defined by spin. We have established the 3 tests that every explanation must pass. On the equator, only on the equator, only on Iapetus. We have watched ordinary geology, volcanoes, tectonics, impacts fail the very first test, because none of those forces respect rotation. We have narrowed the field to 2 families of explanation, both tied to the spin axis. Something about the moon's rotating shape, or something that orbited the moon and fell. We have found, in the moon's huge hill sphere and its strange slow rotation, the special circumstances that might explain why this happened here and nowhere else among the great moons. And we have seen on Pan and Atlas that nature really can build an equatorial ridge by dropping orbiting material onto a world. That last clue is the one that points most sharply forward. Of the 2 surviving suspects, the idea of orbiting material has a particular pull, because we can actually watch a version of it happening elsewhere. If a ring or a disk of debris once circled Iapetus, settled into its equatorial plane, and came raining down, it would have built its wall exactly where we find one, along the equator, and only there. The moon's enormous gravitational territory gave it the rare ability to hold such a ring in the first place. The pieces fit together with a kind of gravitational logic that is hard to ignore. So the equator has done its work. It has taken a baffling, almost otherworldly feature and turned it into a focused question with a short list of answers. The fingerprint points away from random rock and toward the spin of the moon and the things that once moved around it. And the suspect at the very top of that shortlist, the one we can almost see in action on the little ring moons of Saturn, is a vanished ring of Iapetus' own. A band of debris that may have encircled this world long ago and then fallen, grain by grain and boulder by boulder, onto the equator to raise a wall. Now we follow that suspect all the way down. We will examine the strongest version of the story. How Iapetus might have gained a ring or a shattered companion of its own. How that material could have collapsed onto the equator, and what the craters scarring the wall reveal about whether this is really what happened. The ring is the leading explanation for a reason. It is time to find out exactly how it could have built a mountain. Our investigation has come to point at a single, audacious suspect. The equator had eliminated the ordinary culprits, and out of the wreckage of failed explanations, one idea stood taller than the rest: that Iapetus once wore a ring of its own, a band of debris encircling the moon, and that this ring collapsed, raining its material down onto the equator to build the wall we see today. This is, at present, the leading scientific explanation for the ridge. It is not proven. We will be scrupulously careful about that word throughout this part. But of all the ideas on the table, this one passes the 3 locks most cleanly, and it has steadily gathered support over the past 2 decades. So let us follow it all the way down to the surface and see exactly how a vanished ring could leave a mountain behind. First, we need to confront an obvious objection. We have no ring around Iapetus now. Point a telescope at the moon today and you will see a battered, walnut-shaped world with a wall around its waist, but no halo of orbiting debris, no disk of material, nothing circling it at all. So before we can explain how a ring built the ridge, we have to explain where such a ring could have come from in the first place. And then, just as importantly, where it went. The honest version of this hypothesis is not simply a ring fell down. It is a whole sequence of events. A chain reaching back to the violent early history of the moon, and each link in the chain has to hold. The chain begins with a collision. The early solar system was a shooting gallery. In the first few 100 million years after the planets formed, space was crowded with leftover debris, rocky and icy bodies of every size, careening on chaotic orbits, smashing into one another constantly. Every solid world we know bears the scars of that era, and Iapetus is no exception. Its surface is saturated with ancient craters, including those enormous impact basins hundreds of kilometers across. So the idea that Iapetus suffered a major impact early in its life is not exotic. It is almost guaranteed. The question is what such an impact could have produced. When a large enough body strikes a moon, it does not simply punch a hole, it blasts an immense quantity of material off the surface. Pulverized ice and rock thrown upward with tremendous force. Most of that ejected material either escapes into space or falls straight back down. But some fraction of it, launched at just the right speeds and angles, does not escape and does not immediately fall. Instead, it goes into orbit around the moon itself. It becomes a cloud of debris circling Iapetus, held in place by the moon's gravity. And here we return to that crucial fact from the last part. Iapetus, far out at the edge of Saturn's domain, commands an unusually large gravitational territory, the largest, relative to its size, of any major moon out there. So, unlike most moons, which would have their orbiting debris quickly stripped away by their planet, Iapetus could hold on to such a cloud. The remoteness that made it lonely also made it capable of keeping a ring. Now, what happens to a cloud of debris orbiting a moon? Two things, depending on how far out the material sits. And the dividing line between them is a concept called the Roche limit. The Roche limit is the distance within which a body's tides are so strong that they tear orbiting material apart faster than that material's own gravity can pull it together. Think of trying to hold a loose handful of sand in a gale. Below a certain point, the wind scatters the grains faster than your fingers can close around them. Inside the Roche limit, for Iapetus, somewhere in the neighborhood of 2.5 to 3 times the moon's radius, orbiting debris cannot clump up into a single new moon. The tides keep shredding any clumps that try to form. So the material is forced to spread out into a flat, broad ring. Exactly the way Saturn's own great rings are kept flat and smooth because they orbit within Saturn's Roche limit. Outside the Roche limit, by contrast, the tides are gentle enough that debris can gather itself together into a solid body. A sub-satellite, a moon orbiting the moon. This fork in the road gives us 2 related versions of the ring story, and the leading models tend to weave them together. In one version, the impact debris that ends up inside the Roche limit immediately forms a ring around Iapetus's equator. In a second, more elaborate version, Some of the debris ends up farther out, beyond the Roche limit, and coalesces into a small sub-satellite, a little companion moon. That sub-satellite then has its own fate, and its fate, it turns out, can drive the whole process of building the ridge. Here is where one of the more remarkable proposed mechanisms comes in, and it is worth walking through slowly because it ties together several threads. Suppose Iapetus, early on, had a small sub-satellite orbiting it. Over time, the orbit of that sub-satellite would change. We need to recall something from the moon's profile. Iapetus today spins with extraordinary slowness, once every 79 days, but there are strong reasons to think it once spun much faster and was gradually braked by Saturn's tides. A slowing we will examine closely in the next part. As Iapetus despun, slowing from a fast early rotation toward its current crawl, the gravitational relationship between the moon and its little companion shifted. In one detailed model, once Iapetus had slowed enough, the sub-satellite's orbit began to decay. The companion spiraled inward, drawn closer and closer to the moon, like a coin dropped into one of those spiral funnel wells you see collecting donations, circling, sinking, circling, sinking. But why would the companion fall inward at all? Orbits do not simply decay on their own. Something has to drive them. And the driver in this model is the very despinning we keep returning to, through a piece of tidal physics that is worth understanding, because it is the hidden engine of the entire ring story. When a moon spins faster than its companion orbits, the moon raises a tidal bulge on itself, and that bulge, dragged along by the rapid spin, runs slightly ahead of the companion. The bulge is a concentration of mass, and its gravity tugs the companion forward, feeding it energy and pushing it gradually outward. This is not hypothetical. It is exactly what happens between Earth and our own moon right now. Our planet spins faster than the moon orbits, so our tidal bulge runs ahead and nudges the moon away from us by a few centimeters every year. Now, reverse the situation. As Iapetus despun, its rotation slowed until the moon was turning more slowly than the companion was orbiting. The bulge no longer ran ahead, it now lagged behind. And a lagging bulge tugs backward instead of forward, draining the companion's orbital energy rather than feeding it. The same tidal coupling that once pushed the companion away now became a brake, dragging it down. The companion began to spiral inward, slowly at first, then faster, falling toward the Roche limit and its destruction. This is the link the whole story turns on. The slow rotation of Iapetus is not just a curious fact sitting beside the ridge. It is the mechanism that delivered the ring to the equator in the first place. Despinning flipped the tides from a push into a pull, and the pull brought the wall down. And as it crossed inside the Roche limit, the tides of Iapetus seized it and tore it apart. The sub-satellite was shredded into a ring of debris, and that ring, orbiting in the equatorial plane, then deorbited onto the surface, coming down along the equator to build the wall. There is even a proposed reason why no remnant of this companion survives today. In some versions of the model, the same tidal forces that drove material down onto the equator also pushed the outer portions of the system away, so that after the ring had done its work and built the ridge, any leftover body was flung outward and escaped the moon's grip entirely. The ring built the wall and then vanished, partly by falling and partly by fleeing. It is an elegant idea precisely because it accounts for the absence of any ring or sub-satellite now. The structure that built the ridge was meant to be temporary. It was always going to disappear. A related model ties the whole episode even more tightly to a single catastrophe. A giant impact that simultaneously knocked Iapetus into a faster spin, generated the debris, and set the stage for despinning and ridge formation all at once. In that picture, the collision is the origin of everything strange about the moon. Its debris ring, its altered rotation, and ultimately its equatorial wall, bound together as consequences of one ancient violent day. Whether the ring came from a shredded subsatellite or directly from impact debris, the common thread in all these exogenic models is the same. Material that once orbited Iapetus in its equatorial plane came down onto the equator and piled up. It is worth pausing to recognize that the exogenic camp is not a single theory, but a family of related ones, and they differ in ways that matter. The earliest version simply proposed that Iapetus, with its great gravitational reach, once had a ring, and that the ring came down. A second version tightened the picture, arguing that the crucial material was bound closely to the moon, held within the Roche limit where it could never have coalesced into a satellite, and so was always destined to spread into a ring and fall. A third version is the sub-satellite decay model we have just walked through, in which a companion forms farther out, survives for a time, and is only later driven inward and shredded. And a fourth ties everything to a single giant impact that knocks the moon into a fast spin, generates the debris, and sets the despinning in motion all at once, so that the fast rotation, the ring, and the eventual wall are all consequences of one catastrophic day. These are not interchangeable. They predict different timings, different amounts of material, and different relationships between the ridge and the moon's rotational history. Sorting out which of them, if any, is correct is part of why the problem remains open. The exogenic idea wins the argument against the endogenic camp more easily than its own internal variants win the argument against one another. Now let us check this idea against our three locks, because the appeal of the ring hypothesis is how naturally it satisfies them. The first lock, the ridge, sits on the equator. We covered the deep reason in the last part, so we will state it briefly here rather than belabor it. Material orbiting a slightly flattened spinning body gets herded by the body's equatorial bulge into the equatorial plane. By the time a ring is ready to fall, it lies flat in that plane, and so it can only come down along the line directly beneath it, the equator. A ring deposits its cargo on the equator not by choice, but by geometry. The first lock clicks open. The second lock, the ridge, sits only on the equator. This too falls out for free. Since the ring lies entirely in the equatorial plane, there is no orbiting material anywhere else to fall anywhere else. The poles get nothing. The mid-latitudes get nothing. Only the strip directly under the ring receives the rain of debris. A falling ring cannot build a wall across the poles, because there was never any ring over the poles to begin with. The exclusivity that doomed the random geology theories is, for the ring hypothesis, simply built in. The third lock, only Iapetus. Here, the ring model leans on everything we established about the moon's huge gravitational territory and its remote orbit. Among the great moons, Iapetus is the one best positioned to have held a ring or a sub-satellite long enough for this to play out. The inner moons, gripped tightly by Saturn, could not have kept such systems. So the rarity of the ridge maps onto the rarity of the circumstance. There is also a tantalizing connection to the tiny ring moons we met last time. We will not re-explain them, but it is worth recalling that nature already shows us equatorial ridges built by orbiting material falling onto a moon's equator in gentle miniature on those little bodies embedded in Saturn's rings. The mechanism is not a fantasy invented to explain Iapetus. It is a real, observed process demonstrated elsewhere. Iapetus would simply be the same process run at monstrous scale, long ago. So the ring hypothesis passes all three locks, and that is precisely why it leads the field. But passing the logical tests is not the same as being confirmed by evidence. A hypothesis that merely could explain the ridge is interesting. A hypothesis that makes a specific, testable prediction about the surface, which we can then go and check, is science. And the ring model does make such a prediction. It concerns the age of the ridge, and to test it, scientists turn to the oldest trick in planetary geology, counting craters. Craters accumulate on an exposed surface the way dust settles on an untouched shelf. The longer a surface sits exposed to the steady bombardment of space, the more craters it gathers. Count the craters on a patch of ground, and you can estimate how long that ground has been sitting there. A heavily cratered surface is old. A lightly cratered surface is young, because something must have recently resurfaced it, wiping the older craters away. This is one of the most powerful tools we have for reading the relative ages of features on worlds we cannot visit. And it gives us a way to test the ring story directly. Because here is the key prediction. If the ridge was built by debris falling out of the sky and piling onto the equator, then the surface of the ridge was created later than the original surface of the moon. The wall is, in effect, a fresh deposit laid down on top of the ancient terrain, and a feature laid down later should, all else being equal, carry a slightly younger crater record than the ground it sits upon. So researchers counted. They mapped the craters on the ridge and compared them against the craters on the surrounding plains, looking for any difference in age signature, and what they found was subtle but real. A careful study published in 2021 examined the crater populations on and around the ridge and reported an intriguing pattern. The ridge appeared to be depleted in large craters, those bigger than about 16 kilometers across, while carrying an abundance, even a saturation, of smaller craters under that size. One natural reading of this pattern is that the ridge is a relatively younger surface. If the wall had been built after the era of the largest, most ancient impacts, it would have missed out on collecting those giant craters, while still accumulating plenty of the smaller ones over the long ages since. In other words, the crater record is consistent with the ridge being younger than the rest of Iapetus. Exactly what you would expect if it were an exogenic deposit. Material dropped from above onto an older surface. It is worth being precise about what that crater pattern means, because the logic is subtle. A surface that has existed since the very beginning collects craters of all sizes, including the rare, enormous ones thrown by the giant impactors that were common only in the earliest era. A surface created somewhat later, after that first violent epoch had passed, misses its chance to catch those giant impacts, but still accumulates the smaller, more frequent strikes that have continued ever since. So, a deficit of large craters paired with an abundance of small ones is the signature of a surface that formed after the heaviest early bombardment, but has been exposed for a very long time since. That is exactly the fingerprint you would expect from a ridge built by infalling debris early in Iapetus's history, yet not at the very dawn of it. The pattern fits the ring story, but it is an interpretation of a statistical signal, not a direct reading, and the same crater counts can be argued over. A fresh deposit can bury and erase older craters, and a nearby large impact can shower a region with secondary craters that mimic a younger age. The crater evidence leans toward the ring. It does not close the case. The morphology and the cratering, taken together, were interpreted as favoring an exogenic origin. The wall as a thing that fell, not a thing that pushed up from within. We must be careful here, because this is a place where it would be easy to overstate. The crater evidence does not prove the ring hypothesis. Crater counting is a notoriously delicate art, full of pitfalls, distinguishing genuine impact craters from other pits, accounting for the way a fresh deposit can bury and erase older craters, untangling the steady rain of debris from secondary impacts thrown up by larger strikes nearby. Different teams analysing the same surfaces have sometimes reached different conclusions. What the 2021 analysis offers is support, a piece of evidence that points in the direction of an exogenic, younger ridge. It nudges the scales. It does not slam them down. But in a field where every clue is hard-won, a crater signature consistent with a ring origin is a meaningful result, and it has strengthened the case considerably. There is a second strand of evidence, and this one comes not from the moon's surface, but from the laboratory and the computer. A skeptic might reasonably ask whether falling ring material could really build a mountain at all. Debris raining down from orbit does not sound like it should pile up into peaks more than a dozen kilometers high. Falling material tends to splat, to scatter, to blast craters rather than to build towers. So could a deorbiting ring actually construct positive topography? A raised ridge rather than just churning up the ground? To test this, researchers ran detailed impact simulations, modeling what happens when ring debris comes down onto a moon. And the crucial insight was about the geometry of the fall. Material collapsing out of an equatorial ring does not come straight down like a dropped stone. It arrives at a very shallow, grazing angle, skimming almost parallel to the surface, because it is essentially orbiting material losing altitude gradually. It comes in low and slow. The simulations explored exactly this regime. Projectiles ranging from a single meter up to about a kilometer in size, striking at speeds around 400 meters per second, at angles of only 1 to 10 degrees above the horizontal, barely more than a graze, and the results were encouraging for the ring hypothesis. Such extremely low angle, low velocity impacts, the modelling suggested, really can build up positive topography rather than excavate it. Material delivered at a shallow grazing angle tends to pile forward and accumulate, layer upon layer, raising a ridge rather than blasting a hole. Both single impacts and repeated accumulating impacts were examined, and the conclusion was that the gentle, raking in fall expected from a collapsing debris disk is the kind of process that could construct a wall. So the mechanism survived a serious physical test. A ring coming down the way a ring would actually come down, low, slow, and grazing, could plausibly build a mountain. At this point, the ring hypothesis is looking strong. It passes all three locks. It is supported by a crater signature consistent with a younger, deposited ridge. It is backed by simulations showing that low-angle ring infall can raise topography rather than destroy it. And it has a real-world demonstration of the underlying principle on the small ring moons of Saturn. If this were a courtroom, the prosecution would have built a serious case. But good science does not stop at the strongest argument for a conclusion. It goes looking for the problems, the loose threads, the observations that do not quite fit. And the ring hypothesis has them. It is the leading explanation, not the proven one. And intellectual honesty requires that we lay out where it struggles. The most pointed challenge concerns the shape of the ridge's flanks, and it hinges on a concept called the angle of repose. Pour dry sand onto a table, and it forms a cone. No matter how carefully you pour, the sides of that cone will not exceed a certain steepness. A maximum slope angle that loose, granular material can hold before it slumps and avalanches. That maximum is the angle of repose. Now, here is the difficulty. If the ridge of Iapetus were built by debris simply piling up, raining down and accumulating like sand poured onto a surface, you would expect its flanks to sit right around the angle of repose. As steep as loose piled material can manage, but no steeper. Yet when researchers measured the slopes of the ridge, they found something awkward. In places, the flanks are less steep than the angle of repose. They are gentler than a freshly piled heap of debris should be. One analysis raised exactly this objection, arguing that because the ridge's sides are shallower than a pile of accreted material ought to be, a straightforward infall origin is hard to sustain. If the wall were just dumped debris, why are its slopes too gentle? This is a genuine problem, and it has not been waved away. But neither has it sunk the hypothesis, because subsequent work pushed back. Later modelling found that the infall scenario could still be made to work, that under a range of conditions, deorbiting material could produce a ridge whose final form is consistent with what we observe, including its slopes. The flanks might have been modified after they formed, gentled by later processes over the long ages, by slumping, by the relentless erosion of countless small impacts, by the slow downhill creep of material on an ancient surface. A wall built billions of years ago does not keep the sharp profile it had on the day it formed. So the angle of repose objection is best understood not as a fatal blow, but as an unresolved tension. A real observation that the ring hypothesis must accommodate, and that it can plausibly accommodate, though not without some additional assumptions. And that phrase, additional assumptions, points to the broader, more philosophical difficulty with the entire exogenic picture. The kind of difficulty that hangs over every model of this ridge. We will not dwell on it here, because the deeper reckoning with uncertainty belongs to the final part. But it must at least be named. Each version of the ring story requires a specific sequence of fortunate circumstances. You need the right impact, producing the right amount of debris at the right distance. You need a subsatellite to form, or a ring to settle in the right place. You need the despinning to happen on the right timescale to drive the orbit inward. You need the material to come down at the right shallow angles to build rather than destroy. Each step is physically reasonable on its own, but the more steps a story requires, the more it asks of luck, and the harder it becomes to say with confidence that this is what happened, rather than merely what could have happened. The ring hypothesis is the front runner not because it has been proven, but because it fails less and explains more than its rivals. That is a real distinction, and an important one. It is also not the same as certainty. So where does this leave us? With a leading explanation that is genuinely compelling and genuinely incomplete, the ring model gives us a coherent story in which an ancient collision spawned a ring or a doomed subsatellite around the one large moon remote enough to hold it. in which despinning drove that material down onto the equatorial plane, in which the debris rained onto the equator at grazing angles and piled into a wall, and in which the whole apparatus then vanished, leaving only the mountain behind. It is supported by a crater record consistent with a younger, deposited ridge, and by simulations showing the mechanism is physically possible. It satisfies all three of the constraints that destroyed the ordinary explanations, and it stumbles, honestly, on the gentleness of the ridge's slopes and on the sheer number of fortunate steps it requires. But notice something. Every version of the ring story we have told leans at some crucial moment on the same underlying fact about Iapetus, that the moon once spun far faster than it does today, and was then dramatically slowed. The despinning drives the subsatellite inward. The despinning is bound up with the giant impact. The fast early rotation is what makes the whole sequence move. We have been treating that fast then slow rotation as a supporting character, a piece of machinery that makes the ring model run. But what if it is not merely supporting machinery? What if the rotation of Iapetus is not just the engine behind the ring hypothesis, but the heart of a completely different explanation? One in which no ring ever fell, and the wall instead rose from within, a frozen fossil of the days when this moon spun like a top? That is the rival waiting just ahead. We have followed the thing that fell from the sky as far as it will take us. Now, we turn the story inside out, and ask whether the wall came not from above, but from below, and whether the answer to the whole mystery has been hiding, all along, in the way Iapetus turns. Now, we turn the whole story inside out. So far, we have been chasing the idea that the wall came from above, that something fell from the sky and piled onto the equator. But every version of that story leaned at some hidden hinge on a single fact about Iapetus, that this moon once spun far faster than it does today, and was then dramatically slowed. We treated that fact as supporting machinery. Now we promote it to the lead, because there is a whole second family of explanations in which no ring ever fell, no subsatellite was ever shredded, and the wall instead rose from within, a permanent scar left behind by the days when this moon whirled at a furious pace. These are the endogenic models, the inside-out explanations, and to understand them we have to begin with the strangest confirmed thing about Iapetus that we have not yet fully reckoned with: its rotation. Recall the number from the very first part. A single day on Iapetus lasts a little over 79 days. The moon turns once on its axis in the same long span it takes to circle Saturn. It is tidally locked, one face forever toward its planet, rotating with a slowness that is extreme even among locked moons. This is not in dispute. It is one of the firmest measured facts about the world. But here is the crucial inference that follows, and it is an inference, not a direct observation. Iapetus almost certainly did not start out this slow. Worlds are generally born spinning quickly, set turning by the swirling, colliding processes that assemble them. A moon does not condense out of the early solar system already crawling along at one rotation every 11 weeks. It begins fast and is braked over time by the tides of its planet, which act as a relentless drag on its spin. So the 79-day day we measure today is the end state of a long deceleration. Sometime in the deep past, Iapetus turned much, much faster, and then Saturn's tides wound it down, the way a spinning top, left alone, slowly loses its energy and settles towards stillness. That deceleration has a name: despinning, and it is the engine of the entire endogenic story. To see why, we need to recall what fast rotation does to a body's shape, a point we established earlier and will now put to work. A rapidly spinning world flings its midsection outward and flattens at the poles, swelling into an equatorial bulge. The faster the spin, the larger the bulge. So a young, fast-spinning Iapetus would have been markedly bulged at the equator, wider around its waist than around its poles, distended by the centrifugal effect of its own rapid turning. As it despun and slowed, that bulge should have relaxed. A slowing body wants to settle back toward a rounder shape, drawing its equatorial swell back in as the centrifugal stretching fades. And on most worlds, that is exactly what happens. The shape tracks the spin. But what if it could not? What if Iapetus spun fast, bulged out, and then, before its slowing rotation could pull that bulge back in, the moon froze, hardening into rigidity while still wearing the wide-waisted shape of its faster youth? Then, the bulge would be stuck. It would become a permanent feature, a frozen memory of a rotation that no longer exists. Scientists call this a fossil bulge, a body's preserved record of how fast it once turned, locked into its shape long after the spin that created it has died away. Think of a lump of clay spun up on a potter's wheel into a wide, flaring shape, and then fired hard in a kiln before the potter can reshape it. The wheel has long since stopped. The clay no longer turns, but the fired pot keeps the flared form the spinning gave it permanently. The shape outlives the motion that made it. This is the heart of the leading endogenic explanation, and it is a genuinely beautiful idea. In this picture, the equatorial bulge of Iapetus, the broad swelling that gives the moon its overall walnut shape, is a fossil of an early, rapid rotation, and the ridge running along the crest of that bulge would be intimately related to it. A structure raised along the equator as the moon's outer shell adjusted, fractured, or buckled while the body settled and stiffened. No falling ring required. The wall, in this story, is not something deposited onto the equator from orbit. It is the equator itself, pushed up from within and then frozen in place, a line of mountains marking the seam where a fast-spinning moon hardened before it could relax. But this idea, attractive as it is, carries a heavy and very specific price. And the price turns out to be one of the most remarkable claims in the whole study of Iapetus. For the fossil bulge to survive, the timing has to be almost impossibly tight. The moon must have cooled and hardened fast enough to lock in the bulge before despinning erased it. Yet it must also have stayed warm and pliable, long enough for Saturn's tides to actually slow the rotation down to the present 79 days. Cool too slowly, and the bulge relaxes away, the fossil is never preserved. Cool too quickly, and the moon freezes solid while still spinning fast, and it would never have despun to its current crawl. The body has to thread a needle, rigid enough to keep its shape, soft enough to lose its spin, and it has to do both in the right order. To make those competing demands work, the models require that Iapetus was heated in a particular way early in its life, heated by the decay of radioactive elements packed into it when it formed. And here is where the calculation produces something startling. The amount of internal heat needed to thread that needle points in the leading analyses toward a specific heat source, the radioactive decay of an isotope called aluminum-26. Aluminum-26 is a short-lived radioactive form of aluminum that releases heat as it decays. The word short-lived is doing enormous work here. This isotope decays quickly, on a timescale of hundreds of thousands of years, which means it was only abundant in the very earliest era of the solar system, right after the first solid bodies began to form. Within a few million years, it had almost entirely decayed away, and any world assembled later would have missed it. So if Iapetus needed aluminum-26 to heat its interior, and pull off the fossil bulge trick, then Iapetus must have formed while that isotope was still plentiful, which is to say, extraordinarily early. The model suggests the moon must have come together only about 2 million years after the first asteroids began to form, near the very dawn of the solar system's solid history. Sit with the strangeness of that conclusion. The endogenic story, if it is correct, does not merely explain a mountain range, it uses that mountain range as a clock. The very existence of the wall, in this interpretation, would tell us when Iapetus was born, and the answer would place its formation in the first heartbeat of planetary history, earlier than we might otherwise have guessed. The ridge becomes a fossil not just of a vanished rotation, but of the moon's own birth date. This is what makes Iapetus such a profound object. It is a small, frozen, half-forgotten moon at the edge of Saturn's realm, and yet locked into its shape may be a record of conditions in the solar system more than 4.5 billion years ago, written in mountains. But, and we must keep saying this word because the honesty of the whole investigation depends on it. This is a hypothesis, not a confirmed fact. The fossil bulge idea is elegant and it is taken seriously, but it has its own troubles, and they are not minor. The most stubborn problem is the same one that haunts the ring story from the opposite direction. It explains the broad bulge more naturally than it explains the narrow ridge. A fossil bulge accounts beautifully for why Iapetus is wide-waisted overall, why it bulges so broadly at the equator. What it does not obviously explain is why, on top of that broad swelling, there sits a sharp, towering, narrow line of mountains. A frozen bulge is a gentle, planet-wide distension. The ridge is a knife edge, a concentrated wall rising kilometers above its own surroundings. Getting from a smooth fossil bulge to a sharp fossil ridge requires extra machinery, some additional process that focuses all that equatorial stress into a tight band rather than spreading it across the whole midsection. And supplying that focusing mechanism in a way that works has proven difficult. This is where the other endogenic models enter, each trying to provide the missing focus, and each running into its own wall. Consider the tectonic idea. The notion that the ridge was pushed up by stresses in the moon's outer shell, its lithosphere. One version proposes that as Iapetus's interior cooled and contracted, the whole body shrank slightly, and that global shrinkage squeezed the crust, buckling it upward. A detailed proposal along these lines argued that contraction, driven by the closing of tiny pores in the moon's interior as it heated and compacted, could generate the necessary squeezing, especially if the crust were thinner along the equator and so more prone to buckle there. Another careful analysis showed that compressing a shell of uneven thickness, one locally thinned at the equator, really can produce a narrow uplift resembling the observed ridge. The mechanism is physically interesting, but it comes with a catch that keeps recurring in this subject. To raise a ridge by purely elastic buckling, you need stresses along the north-south direction that exceed the strength of the ice itself, stresses large enough that the ice should fail rather than fold cleanly. And you still need a separate reason why the deformation focuses on the equator in the first place, rather than appearing wherever the crust happens to be weakest. The tectonic models, in other words, require special and finely tuned conditions. They can be made to work, but only by constraining the moon's early state quite precisely. A sweeping survey of the endogenic possibilities reached a sobering verdict. When researchers examined the internal mechanisms on their own, tectonics, volcanism, the various ways a moon might push up a ridge from inside, they did not find a likely purely internal origin for this particular landform. That is a significant statement, and it deserves to be heard plainly. The most thorough look at the inside-out explanations concluded that none of them, by itself, comfortably produces what we see. The endogenic family is rich with ingenious ideas, but each one leaves a residue of unexplained difficulty. There is one more inside-out idea worth naming, because it is genuinely different in flavor. Convective overturn, with the ridge held up by deep roots. This proposal treats the bulge and ridge the way geologists treat mountains on Earth, as features in what is called isostatic equilibrium. The principle is the one that governs an iceberg. An iceberg floats with most of its bulk hidden below the waterline. The towering part you see above the surface is balanced, buoyed up, by the much larger mass submerged beneath. Mountains on a planet can work the same way. A mountain range can stand tall because it sits atop a deep root of low-density material that floats it upward, the way the unseen base of the iceberg floats the visible peak. In this version of the Iapetus story, the equatorial bulge is held up by exactly such roots. Regions of less dense material beneath the surface, their buoyancy supporting the weight of the wall above. The ridge, in this telling, would be built of lighter matter, raised and sustained by slow churning motions in the moon's interior. Perhaps a pattern of convection that organized material along the equator. It is a creative idea, and it ties the ridge to processes we understand from other worlds. But like all its endogenic cousins, it must still answer the relentless question of focus and exclusivity. Why this band? Why the equator? Why only here? And it does not answer them decisively. There is one more endogenic variant that sits close to the fossil bulge idea, but is worth distinguishing, because it sharpens what fossil might mean. Rather than picturing a bulge that froze and then had a ridge added to it, this version imagines Iapetus spinning early on at a near critical rate, fast enough that the moon was on the verge of the rotational speed at which a body begins to fly apart. At such an extreme spin, the equatorial region is pushed outward so violently that the shape becomes sharply peaked at the equator rather than gently swollen. And if the lithosphere then cooled and stiffened while the moon was still turning at that near critical rate, it could lock in not just a broad bulge, but a genuinely ridge-like equatorial form. A separate proposal invokes a two-cell pattern of convection in the interior. Two great churning circulation cells organizing the moon's internal flow in a way that concentrates uplift along a single equatorial band. Each of these is an attempt to solve the focusing problem that defeats the simpler fossil bulge picture. The challenge of turning a gentle, planet-wide swelling into a narrow, towering wall. And each, like every endogenic idea, must still explain why the result appears on Iapetus and on no other large moon, since plenty of moons spun fast when young and plenty have convecting interiors. So, step back and survey the whole battlefield, because this is the moment to be completely clear about where the science actually stands, and to resist the temptation to declare a winner the evidence does not support. We have two great families of explanation: the exogenic family, the ring, the shredded subsatellite, the material that fell from orbit. passes the 3 locks cleanly, draws support from a crater record suggesting the ridge is younger than the surrounding terrain, and is backed by simulations showing that low-angle infall can build rather than destroy topography. It stumbles on the gentleness of the ridge's slopes and on the sheer number of fortunate steps it requires. The endogenic family, the fossil bulge, the tectonic buckling, the buoyant roots, explains the moon's broad shape with real elegance, and even offers to date the moon's birth, but struggles to concentrate a gentle bulge into a sharp wall. And the most careful surveys have failed to find a purely internal mechanism that works without straining. Here is the honest verdict, and it is the only one the evidence supports. No single explanation has been conclusively proven. This is not a failure of the scientists. It is the nature of the problem. The event that built the wall, whatever it was, happened more than 4 billion years ago, in a moment we cannot rewind and cannot rerun. We were not there. No instrument recorded it. We are detectives arriving at a scene billions of years cold, holding a single frozen artifact and trying to reconstruct the vanished process that left it behind. The leading hypothesis, the front runner, the one that currently fails least, is the exogenic ring story, because it satisfies the constraints most naturally and carries a thread of supporting evidence in the craters. But leading is not the same as proven, and a responsible account refuses to pretend otherwise. The wall could be a fallen ring, it could be a fossil of a faster spin, it could be some combination of the two, a ridge whose raw material came from orbit, but whose final shape was sculpted by the moon's own settling, or a fossil structure later dusted and modified by infalling debris. The most likely truth may not be a clean victory for either camp, but a braided history we are still learning to read. And we should be candid about one more thing, because it shadows every model on both sides. Each of these explanations, exogenic and endogenic alike, requires a chain of specific and somewhat lucky conditions. The ring story needs the right impact, the right debris, the right despinning, the right grazing angles. The fossil bulge story needs the right radioactive heating, the right cooling rate, the right timing caught within an impossibly narrow window. Both stories ask us to believe that a particular sequence of events, none of them common, all lined up just so on this one moon. That is, in a sense, exactly what we should expect, because the wall itself is unique. Of all the hundreds of moons in the solar system, only Iapetus wears one. A unique feature demands a uniquely specific history. The very rarity of the ridge is a clue that whatever made it was rare, a confluence of circumstances that happened here and, so far as we can tell, nowhere else. The difficulty of explaining the wall and the singularity of the wall are not two separate problems. They are the same problem, seen from two sides. This raises a question that the debate cannot avoid. If the evidence is genuinely divided, what would it actually take to settle it? The answer points to measurements we do not yet have. The cleanest test would come from the moon's interior. The fossil bulge and the buoyant root models make specific predictions about what lies beneath the ridge, whether there are deep concentrations of low-density material supporting the wall from below, or whether the moon's mass is distributed in a way that betrays an ancient, faster-spinning shape locked into its core. Mapping that interior structure would require precise tracking of how Iapetus's gravity tugs on a passing spacecraft, dense enough to model the moon's insides rather than just its surface. The ring models, by contrast, would be tested by composition. If the ridge were built from infalling debris, its material might differ subtly from the terrain it sits upon, and detailed spectroscopy along and across the wall could reveal whether it is a foreign deposit or native rock pushed up from within. Even the age question, which crater counting only estimates, could in principle be tightened with higher resolution imaging of the ridge's full extent, including the segments that thin out across the bright hemisphere where our coverage is poorest. The difficulty is that gathering any of this means going back. The Cassini spacecraft, which gave us everything we know about the wall, completed its mission and was deliberately sent to burn up in Saturn's atmosphere in 2017. There is no funded mission on its way to Iapetus, and the moon's great distance from Saturn made it one of the hardest targets, even for Cassini to reach closely. So the wall waits far out beyond Saturn's other moons, holding answers we know how to extract but cannot currently go and collect. The debate is not stalled for lack of ideas about how to resolve it. It is stalled for lack of a spacecraft willing to make the journey. Before we draw this to a close, we should give the moon's other famous feature its due, briefly, and then set it gently back in its place. We have spent 4 parts on the ridge, but Iapetus is also, as we noted at the very beginning, the great two-tone moon, black as coal across its leading hemisphere, bright as dirty snow across its trailing side and poles, with the starkest light-dark contrast of any large body we know. It is tempting to fold this dramatic colouring into the story of the wall, and some early thinking did wonder whether the two were linked, since the ridge runs straight through the heart of the dark region. But the leading understanding today treats the colouring as a largely separate phenomenon, a surface process rather than a structural one. The current picture involves a runaway feedback called thermal segregation, made possible by that extraordinary 79-day day. Because the Iapetus turns so slowly, each point on its surface bakes under sunlight for weeks at a time. Dark material absorbs more heat than bright ice, so any patch that starts out slightly dark warms up more, driving its ices to sublime away and migrate to colder, brighter regions, leaving the dark patch darker and the bright regions brighter, a runaway that sharpens the contrast over time. The dark material itself may have been seeded from outside, a dusting of dark particles possibly drifting in from the distant outer moon, Phoebe and its faint, enormous ring, coating the forward-facing hemisphere as Iapetus plows along its orbit. It is a fascinating story in its own right, but it's a story about paint, not about architecture. The colouring tells us how the moon got its 2 faces. It does not tell us how the moon got its wall. The ridge remains the deeper mystery, and the dark hemisphere is the dramatic backdrop against which that mystery is set, not a replacement for it. There is one more line of evidence we have not yet brought to bear, and it is perhaps the most quietly persuasive of all. Not something Iapetus has, but something its neighbours lack. Iapetus is not Saturn's only large icy moon. It shares the system with a family of comparable worlds, Rhea, Dione, Tethys, and others, bodies built from much the same blend of ice and rock, several of them in the same broad size class, all of them shaped by the same Saturn, the same era, the same relentless early bombardment. And here is the telling fact. Not one of them wears an equatorial wall, not a trace. You can scour the surfaces of every other major moon of Saturn and find craters, fractures, basins, bright streaks, and frozen plains, but nowhere a towering mountain belt tracing the equator. The feature that defines Iapetus exists on Iapetus alone. That absence is not a footnote. It is a constraint, and a sharp one, because those sibling moons had many of the same ingredients we have been invoking to explain the wall. They too were almost certainly born spinning faster than they turn today. They too were braked by Saturn's tides over the ages. So if a fossil bulge from rapid early rotation were all it took to raise an equatorial ridge, some of them should show at least a hint of one. They do not. And the inner moons sit far closer to Saturn, deep in the region where rings and orbiting debris were, if anything, more plentiful, yet none of them caught a ring and brought it down onto their equators to build a wall. The raw materials of both leading hypotheses were available across the whole family. Only one member ended up with the structure. The siblings are a control group that nature ran for us, and they failed to reproduce the result. So what did Iapetus have that the others did not? Everything strange about it converges on the same answer, and we have met each piece already. Its extreme remoteness, orbiting alone far beyond Saturn's other great moons. Its uniquely vast gravitational reach, wider by far than any of theirs, which alone amongst the family could have caught and held a ring or a companion long enough to matter, and its dramatic despinning, the violent winding down from a fast youth to a 79-day crawl, far more pronounced than what his inner siblings experienced. The very things that made Iapetus the lonely, overlooked outermost child. Its distance, its weak tides, its sprawling sphere of influence are precisely the things that set it apart as the one world where a wall could form. Its siblings prove the point by their silence. They had the ingredients and produced nothing because they lacked the specific, peculiar circumstances that Iapetus alone possessed. That silence is the comparison's sharpest lesson. The conditions that built this wall almost never align. And on Iapetus, just once, in this one place, they did. So we arrive, at last, at what this wall really means. And here, finally, is the reflection the whole journey has been building toward. We began with an image that looked edited, a moon that appeared to have been built. And the instinct, staring at that picture, is to feel that the strange thing about Iapetus is how artificial it looks. A seam around a planet, a rampart circling a world. Surely the marvel is that nature produced something that mimics design so convincingly. But that gets the wonder exactly backwards, and unwinding it is the true reward of this entire investigation. The strange thing about Iapetus is not that its equatorial wall looks artificial. We have spent 4 parts dismantling that first impression, and it does not survive contact with the evidence. There are no aliens here, no engineers, no monument. There are only the ordinary, patient, indifferent processes of planetary physics. Spinning matter, falling debris, cooling ice, decaying isotopes, the slow grind of tides. The truly remarkable thing is that those blind, unguided processes, working on a frozen moon at the cold edge of a planetary system, produced something so geometrically clean, so precisely aligned, so striking to the human eye, that we keep wanting to call it a wall. Nature did not build a monument. Nature did something stranger and, in its way, more profound. It left a fossil. That is the word that belongs at the end of this story. A fossil. When we find a fossil in stone on Earth, the creature itself is long gone. Its flesh, its breath, its living motion all vanished hundreds of millions of years ago. What remains is only the shape it pressed into the rock, a record of a life we can never directly observe, preserved by accident in stone. The equatorial ridge of Iapetus is a fossil in exactly this sense. The event that made it, whether a ring spiraling down out of the sky, or a fast-spinning moon freezing before it could relax, or some braided combination we have not yet untangled, that event is over. It happened once, more than 4 billion years ago, in a brief and probably violent chapter of this moon's earliest life, and it will never happen again. The process that built the wall is gone. We cannot see it. We cannot rerun it. We can only stand before the shape it left and try to read backward to the vanished moment that pressed it into the world. And the wall is a faithful keeper of that record. Iapetus, we have learned, is one of the most geologically quiet large poons in the solar system. No internal heat to speak of, no churning activity, no resurfacing. It is, in effect, a frozen relic, a world that locked into its current form long ago and has barely changed since, preserving its ancient face beneath nothing but the slow rain of impacts. That very deadness is what makes it precious. A more active moon would have erased its own history, melting and reshaping and burying the evidence. Iapetus kept everything. The wall has stood on the equator through almost the entire life of the solar system, scarred by craters, gentled by ages, but never destroyed, a structure holding the imprint of an event from the dawn of the planets, carried intact across 4 billion years to the moment a spacecraft finally turned its camera toward it on the last day of 2004. So when you picture Iapetus now, the dark face and the bulging waist, the towering line of mountains tracing 3/4 of the equator, do not see a wall that looks built. See a fossil of something we can no longer watch. See the frozen shape of an ancient process, still fiercely debated, that physics ran exactly once on this one small moon and then put away forever. The competing explanations are not a sign that we have failed. They are a sign of how much this single frozen artifact is still trying to tell us, and how carefully we must listen to read its testimony. We may never be entirely certain which story is true, but the wall will keep its secret patiently, as it has for 4 billion years, waiting at the edge of Saturn's realm. A mountain range that knows where the equator is and remembers a world that no longer exists,